Have you ever thought, could you actually make electricity just by moving something? I mean, it sounds like something out of a sci-fi movie, right? But it's totally real. It's one of the most fundamental principles of our universe. Today, we're going to dive deep into motional EMF, this incredible, fascinating link between motion and electricity.
Okay, so to kick things off, let's start with a little bit of what looks like magic. Just watch this. What you're seeing is a solid metal ring just levitating, and then launching into the air above a coil. Seriously, there are no strings, no hidden jets, nothing. So, what is going on here? What's the physics behind this incredible trick?
That's the big question, isn't it? What invisible force is making this ring fly? And the answer, well, it's going to take us on a journey through one of the absolute coolest concepts in all of physics. And trust me, by the end of this, you'll see exactly how this little magic trick is connected to the very electricity that's powering your screen right now.
All right, it's time to meet the hero of our story, motional EMF. This is it. This is the scientific principle behind our jumping ring, and honestly, so much more.
So, what in the world is motional electromotive force, or EMF for short? Well, put simply, it's a voltage that gets created, or as physicists say, induced, inside a conductor anytime it moves through a magnetic field. Now, this isn't some obscure random rule. It comes directly from Faraday's law of induction, which is one of the absolute pillars of electromagnetism. It was Faraday who figured out that a changing magnetic field creates an electric field, and that right there is the fundamental idea we're going to explore.
Now here's the crucial part. This voltage doesn't just appear because something is sitting in a magnetic field. No, it's all about change. You have to change something called the magnetic flux. Just think of flux as, like, the total number of magnetic field lines passing through a loop. And as you can see here, there are two main ways you can mess with that number. You can either change the area of the loop inside the field, like pushing a rectangle into it, or you can change the loop's orientation, maybe by rotating it. Either way, you're changing the flux, and that's what matters.
Okay, I know that might still feel a little abstract, so to really get our hands dirty with this idea, let's break it down with a classic physics example, the good old sliding rod model.
So here's the setup. We've got a conducting rod, and it's just resting on two parallel metal rails. See how it makes a simple circuit? The whole shebang is sitting in a uniform magnetic field. That's all those X's. And it's pointing straight into the screen. Okay, now watch. What happens when we pull that rod to the right with a constant velocity, v? Well, as it moves, the area of that loop, the rectangle MNOP, it gets bigger and bigger. And what did we just learn? A changing area means a changing magnetic flux, and that right there is the key.
And this whole beautiful relationship is captured in one simple, elegant equation, epsilon equals B times L times V. The induced voltage, that EMF we're talking about, is represented by that Greek letter epsilon. And it depends on just three things: B, the strength of the magnetic field, L, the length of the rod moving through it, and V, how fast it's going. You want a bigger voltage? Well, get a stronger magnet, use a longer rod, or just move it faster. It's simple, it's powerful, and it's incredibly useful.
But wait a second. This brings up a pretty big question. If we can just move a rod and create electrical energy, are we getting something for nothing? Are we creating free energy? Well, you know the answer. Of course not. In physics, energy is never free. It always, always, always has to obey the law of conservation. You see, there's what I like to call a cosmic price tag. When we move the rod, that induced EMF drives a current through the circuit. But here's the catch. A current moving through a magnetic field feels its own magnetic force. And according to something called Lenz's law, this force, we'll call it F sub m, always opposes the motion that created it in the first place. It's like a magnetic friction that's constantly trying to stop you. So to keep that rod moving at a constant speed, you have to apply your own external force F sub a to pull against it. And here's the beautiful part. The mechanical work you do pulling that rod is perfectly one-to-one converted into the electrical energy that then gets turned into heat by the resistor. No free lunch in physics.
Okay, so we've got the principle down in a simple lab setup. Now, let's see what happens when we take this idea and push it to its absolute limits, taking it everywhere from military tech all the way to outer space.
Feast your eyes on this. A rail gun. This is basically our sliding rod experiment on steroids, but running in reverse. Instead of you pulling a rod to create a current, you blast a massive external current through the projectile. And that current, as it interacts with the incredibly powerful magnetic field from the rails, creates an enormous magnetic force that launches that projectile at unbelievable speeds. And when I say massive current, I am not kidding.
For a railgun to actually be an effective weapon, it needs something in the neighborhood of 1 million amps of current. That is the kind of mind-boggling power you get when you apply this principle on a huge scale.
All right, now let's flip from a weapon on Earth to a generator in space. This was the incredible idea behind NASA's tethered satellite experiment. The plan was pretty wild. Unspool a really long conducting wire from the space shuttle. As the shuttle zoomed around the Earth, the wire would be slicing through our planet's own magnetic field, basically acting like a gigantic power generator.
And how long was this wire? An absolutely astounding 20 kilometers. Let that sink in. In our equation, epsilon equals BLV. That massive number is our L, the length of the conductor.
So, by moving at orbital velocity through Earth's magnetic field, this 20-kilometer tether was predicted to generate a staggering 5,000 volts of electricity. Now, full disclosure, the real-life tests back in the 90s unfortunately ran into some technical problems. But the physics was absolutely sound, and it's still a spectacular demonstration of the sheer potential of motional EMF. Okay, so we've seen a jumping ring, a sliding rod, a rail gun, and a space tether. Now it's time for the big takeaway, how this one principle is fundamentally responsible for, well, generating our entire world. Take a close look at this diagram. It's a coil of wire, and it's rotating inside a magnetic field. Does that look a little familiar? It should. It's just our second way of changing magnetic flux from the very beginning. As that coil spins, its orientation to the field is constantly changing. And as we learned, that induces an EMF. This simple setup, this is it. This is the fundamental design behind almost every single electric generator on Earth. Hydropower dams, nuclear power plants, coal plants, they all use some form of mechanical energy, falling water, steam, whatever, to spin a coil in a magnetic field and generate the electricity we use every day.
So really, the whole thing boils down to this. The same physics that launches a toy ring is what powers our cities. That mysterious invisible force that made a little ring jump is the exact same principle we've harnessed to build our entire modern civilization. It's all just motional EMF.
And that kind of leaves us with a final thought to chew on. If simple, everyday motion can be so directly converted into the invisible power of electricity, what other incredible fundamental forces and connections are still out there, just waiting for us to discover and harness them? Thanks for watching.